Hi, my name is Daniel Kalny, and in the following presentation, I am going to talk about a near-field magnetic induction communication system implemented with a GreenArrays chip GA144. Near-field magnetic induction communication is a wireless form of a short-range communication using modulation of magnetic flux for data transmission. The magnetic field energy is transmitted and received through resonant coupling of inductors. Compared to other short-range communication technologies such as Bluetooth, NFMI has much lower power requirements, operates at shorter ranges from centimeters up to couple of meters, and at slower data speeds. A major advantage of NFMI communication over traditional electromagnetic RF-based systems is that the magnetic induction waves are not generally affected by the environment, allowing communication through obstacles such as water, rocks, or human body. Therefore, NFMIC targets the medium-capacity personal area networks with close proximity. There are NFMI technologies using higher carrier frequencies, such as NFC operating at IMS band of 13.56 MHz. Alternatively, long wavelength signals with carrier frequencies below 450 kHz can be used, as is described in an IEEE 1902.1 standard. The physical layer of the NFMIC system shown in this presentation is based on the standard. It uses carrier frequency of 131 kHz, 1024 bits per second data rate, amplitude shift keying modulation, and biphase mark encoding. Frame format is a simplified form of that described by the standard. Each frame starts with 12 synchronization bits, followed by an arbitrary number of 16-bit data words. The frame ends with a CRC using CCITT 8-bit polynomial and a trailing sequence of 8 0 bits. The content of data words does not correspond to the standard definition and is defined by a higher-level protocol. The system presented here is implemented using a GreenArrays evaluation board and a simple communication module. The module has a separate transmitter and receiver circuits. The transmitter uses an op-amp with a positive feedback to amplify voltage generated by an analog node across a load resistor to ground. The voltage gain of the op-amp is about 10. The output of the op-amp is fed into a series LC tank circuit with resonant frequency of 131 kHz. The receiver circuit is very similar to the transmitter. Oscillations of magnetic field create an induced voltage in the parallel resonant LC circuit. The induced voltage is amplified with an op-amp and fed into an analog node. The voltage gain of the positive feedback is about 100. Based on experiments with the circuits, I have later added a parallel 3K3 resistor to the receiving LC tank circuit in order to decrease the quality factor and suppress signal overshoot. The communication module uses the same antennas for transmission and reception. The antennas are made of about 190 turns of enameled copper 31 gauge wire wound in 2 layers around a ferrite rod core. The inductance of each antenna is about 313 microhenry. The op-amp used is a dual CMOS op-amp TLV342 manufactured by Texas Instruments. The two antennas are located on the other side of the PCB. Although the circuit is not an ideal for signal transmission and reception, the advantage is its simplicity, low component count, and the same supply voltage as that for GA144, 1.8 volts. Hence, no level shifters are needed between GA144 and the module. GreenArray chips are by no means ordinary microcontrollers, and it is therefore not surprising that the procedure of their programming also requires unusual methods. The first step in programming a GA chip is to carry out a thorough floor planning. We start with a definition of input-output requirements. An application may need several GPIO or analog pins, or any of the available parallel or serial buses. In any case, we need to locate the nodes with input-output capabilities and perhaps try several combinations to find the optimal locations. As the code in GA chips is often data-driven, the next step is to define logical data paths within the application. The path is defined in such a way as to allow data to enter at the beginning, to be processed along the path, and to exit at the end. Data entering a path are to be processed according to a given algorithm. Such an algorithm has to be decomposed into small pieces of sequential code that can be individually implemented in nodes. For a more complicated code, one can divide the execution between several nodes. In such a case, one node is controlling the code execution while the others are cooperating and execute their code on demand. GA chips also provide for a very efficient method of code execution, so-called port execution. In this case, a node executes a code that is fed into its port by another node. This is a very powerful technique and is often used. A floor plan for the NFMIC system presented here requires one GPIO pin to connect a quartz crystal used to generate the carrier frequency. We also need one analog output for transmitter part of the communication module and one analog input for receiver. Although analog nodes of GA144 include both input and output pins, it is more efficient to split both paths and use two separate analog nodes. The whole system can be divided into three blocks: a clock generator implemented in the node 715, a transmitter path starting at the node 615 and ending at the analog node 717, and a receiver path starting at the analog node 713 and ending at the node 612. The NFMIC system, as shown here, is able to function independently of other code running in the chip. It is sufficient to feed data to be transmitted into the node 615 and to read any data arriving via receiver path from the node 612. The data can be provided by neighboring nodes running an application, via IDE path through an async serial link during the development, or by a polyfourth virtual machine running at the same chip and using ganglion messages to deliver data to and from the NFMIC system. Whatever the method, the system is absolutely oblivious to its nature. Before discussing any code, I will briefly describe a function of individual nodes. The first one is the node 715 functioning as a clock generator. The algorithm for driving a quartz crystal connected as shown here has been described in a GA application node. Here the code has been modified so that the oscillator can be activated and stopped at any time. The oscillator is running only when an NFMI transaction is required and halted otherwise to save the energy. The transmitter path starts at the node 615, implementing a serializer. This node converts an incoming data stream of 16-bit words into a stream of bits, the most significant bit first, and feeds the serial bit stream into the node 616. The node 616 implements a framer, which constructs a frame by prepending synchronization bits in front of the data bit stream, calculates CRC, and appends the checksum at the end of the data stream. Finally, it appends a closing 0-bits sequence. The whole frame is fed on the fly into the node 716, which encodes the incoming bits into marks and spaces according to biphase coding. Finally, the node 717 reads marks and spaces from the node 716 and modulates an output signal with corresponding waveforms by setting its analog output to a predefined voltage or the ground. The changes on the output pin are gated by the shared pin 17 that is internally connected to the pin 17 of the quartz oscillator. The transmission runs until the node 615 is informed about the end of data. Then the frame is closed, and soon the transmission is finished. When the modulator suspends, the whole path is ready for another transmission. The receiver path starts at the analog node 713. The code here emulates a detector of a simple radio receiver. It implements several routines used to calibrate the ADC, to determine instantaneous voltage at the analog input pin, and to measure the maximum amplitude of the incoming signal. It can also provide an information whether there is any signal present at the analog input pin. All these functions are executed when requested by the neighboring node 714. All those requests originate from the node 614. When receiving a signal, the node 714 samples it at a frequency of 8 times the carrier frequency. It then applies a filter to generate an amplitude envelope of the incoming signal. The filtered signal is fed into the node 614, which recognizes rising and falling edges of the envelope and decodes the incoming signal into a stream of bits. Of the three nodes, the node 614 is the one that controls the whole cluster. Other two nodes just execute their code upon a request from the node 614. The stream of bits is then forwarded into the node 613, where data are separated from the rest of the frame and a CRC is calculated. The data bit stream is finally sent to the node 612, which implements a deserializer reconstructing 16-bit data words and making them ready for reading. Since a frame may have an arbitrary length, the system has to know when to stop transmitting or receiving a frame. In order to signal the end of transmitted data, I have exploited a simple fact that GA chips use 18-bit wide words, while only 16 lower bits are used for transmitted data. Therefore, when a word with the bit 17 set high is read by the node 615, it is recognized as the end of data stream and the process of closing the frame starts. On the receiver side, there is no such possibility to indicate the end of frame. Both CRC and the last 80 bits of the frame cannot be distinguished from regular data. Hence, the decoder in the node 614 has a timeout loop which signals the end of frame if there is no amplitude change longer than what corresponds to 2 bits. When it happens, the node 614 stops ADC in the node 713 to save the energy and informs the node 613 of the end of frame. The node 613 then finishes the calculation of CRC and passes the result of the check down the stream with the bit 17 set high to signal the end of frame. This signal is then forwarded by the node 612 as the last data word to any recipient. It's up to the higher level protocol to check the CRC result and to take any further action. One more remark to the receiver data path. The node 612 does not provide any buffering capacity. If at the time of data word availability there is no neighboring node reading the data word is simply discarded in order not to suspend the node 612 and consequently the whole data path. It is the responsibility of the higher level protocol to wait for the data from the node 612. It could be interesting now to have a look at a signal generated by the transmitter and how it looks like when received by the communication module and processed by the receiver path. In order to find out what happens with the signal outside the GA144 chip, an oscilloscope is a tool of choice. As you will see shortly, a GA chip itself can be used as a probe for the same purpose when the signal inside the chip is to be tested. In fact, with GA chips this is a very simple task. Before discussing the measurement results, I'll briefly elaborate on the idea of using a GA chip as a probe to test itself. Due to its modular nature, the code used for the NFMIC system can be easily modified for experimentation with the signal transmission and reception. For a signal generation test, I only needed the oscillator, encoder, and modulator nodes. Instead of reading a stream of bits, the encoder is supplied a required mark and space sequence as a ganglion message. It can be anything from a simple carrier signal to any complicated sequence of marks and spaces. The point is that the exact moment when the sequence starts can be controlled from the polyforth code. A ganglion message can also be used to set a transmitter power. This is the voltage that DAC uses for signal generation. The oscillator itself can be controlled via ganglion messages. The receiver is also simplified so that only detector, sampler and decoder nodes are used. As in the case of the transmitter, we don't need to receive a stream of bits. Rather, we are interested in raw or processed data from the ADC. Therefore, using ganglion messages, we download a stream of numbers from the ADC into a memory controlled by polyforth and then treat the recorded data offline. The advantage of using a chip itself as a test tool is that both transmission and reception of the signal can be initiated in a concerted fashion, and the test software can be written in high-level polyforth, which also runs on the same chip. Thus, the chip contains everything we need to test our design. It should be kept in mind, however, that the transfer function of ADC in GA144 is not linear in the whole range of allowed input voltages. As you can see on this record determined experimentally, the transfer function has a sigmoid shape. For that reason, the signal is distorted and the resolution degraded near the extremes of the acceptable voltage span. Although the ADC does not provide accurate values, it is still useful for visualization of an overall shape of a signal. So the voltages determined by ADC presented in the following records are approximations only. Let's start with the transmitter. For the sake of clarity, the following oscilloscope traces have been generated with a burst of carrier signal lasting for 8 periods only. First, I wanted to check that the output of the analog node 717 is a good square wave signal with correct frequency and amplitude. A snapshot of a scope screen confirms the generator works correctly. I was also interested to see how the signal is modified by the LC resonance circuit. A signal measured with an oscilloscope between inductor and capacitor is shown in the second picture. It is worth to note the slowly rising and falling edges of the transmitted signal envelope. Also, a ringing of the LC tank circuit is visible as the signal is longer than the driving square wave burst. The oscillations visible at the start of the trace come from a pulse sent to trigger the oscilloscope and are not related to the signal itself. On the receiver side of the module, I have recorded a scope trace at the output of the op-amp. The recorded signal is rectified due to a non-symmetrical power supply of the op-amp. The ringing of the signal is even more enhanced here. Again, the signal at the beginning of the trace comes from the triggering pulse. Interestingly, the trace recorded with an oscilloscope can be compared with the same signal recorded by the GA chip itself. As you can see, the overall shape of the recorded traces is very similar. This confirms that the chip itself can be used to record the received signal. In the following part, I am using a full-length signal of 128 oscillations of the carrier as only an envelope of the signal is significant. The raw signal as received by the module and digitized by decoder node is shown in the first recorded trace. A detailed profile of the same signal is depicted in the second picture. Each point represents a single value determined by ADC. As noted earlier, the sampling rate is 8 times the carrier frequency. At the beginning of signal reception, the detector node determines an amplitude by taking 8 samples and looking for the maximum voltage. The value is used later for signal decoding, as I will explain shortly. The received signal is then passed through a digital filter. The filter is based on a simple algorithm. First, a difference between the last filtered value and the current raw signal value is calculated. Then, when the signal is rising, the difference is added to the last filtered value to get a new one. Thus, the signal is passed through the filter without any modification. On the other hand, when the signal is going down, a factor of 1/16 is used to slow down the decline. This way, an amplitude envelope shown here is obtained. The residual oscillations do not cause any complication in further signal processing, as will be shown in a short time. A detail of the signal after filtration is shown here. The advantage of this algorithm is that only fast right-shift instructions are used to get the reduced signal value. The next task of the decoder is to determine the length of signal between two consecutive edges. Thus, I have implemented a software analog of a Schmidt trigger and a pulse width measurement. The amplitude value determined earlier is converted into an upper and lower hysteresis limits. The calculation is again simple and fast, as the limits are set as 1/4 and 3/4 of the maximum. Then the code in the detector compares the current filtered signal value with these two limits and records the moment when the value exceeds the upper limit during rise of the signal, or the current value goes below the lower limit when the signal is falling. This way, the signal envelope is converted into a square wave. It is a simple matter of counting the number of samples between the square wave edges to determine whether a 0-bit or a 1-bit is being received. According to the biphase mark coding, a 0 is coded as a mark or space of a duration of 1 clock cycle, while a 1-bit is coded in such a way as to have a level change in the middle of the bit. This coding was the original frequency modulation in single-density floppy disks. The advantage of the coding is that when marks and spaces are exchanged, the code is still valid. This is important in NFMIC, as rotating the ferrite antenna by 180 degrees changes the direction of the magnetic flux and consequently the polarity of the signal received. To determine out of the BMC signal whether a 0 or 1 bit is being read, the decoder counts the number of samples between two edges. As the data clock period is 128 carrier cycles per bit, at the sampling rate of 8 times the carrier frequency, the bit length corresponds to 1024 samples. If the count is greater or equal to 3/4 of this number, this is 768 samples, the bit is considered 0. On the other hand, if the count is lower than that number, a level of the signal is taken into account. When the signal went high, then the count is ignored and the second interval is counted. When the signal went low, the bit is considered as 1 and the next interval is ignored. The counter restarts each time an edge is detected. The 3/4 limit for distinguishing between 0 and 1 bits is sufficient to provide for a high robustness with respect to differences in carrier frequency and the sampling rate. This is necessary as the asynchronous nature of GA chips prevents an exact time measurement using 4 next loops. The same experimental setup has also been used to determine how far the signal can reach and what is the effect of transmitter DAC amplitude on the reach of signal. The first graph shows a dependence of signal intensity, measured as the maximum amplitude of the received signal, on the distance between antennas. The experiments were carried out at different transmitter DAC output amplitudes. The measured data confirm the fact that the signal in the near field has a sharp roll-off decaying as an inverse sixth power of distance. This is why the NFMIC is well suited for private data transmission in a so-called secured communication bubble. Moreover, it promotes frequency reuse over short distances and also contributes less interference with other existing radio frequency communication systems. The next graph then shows the reach of the signal, defined as the distance of a 6 dB signal attenuation versus the transmitter DAC amplitude used. Increasing the DAC amplitude increases the reach of signal. However, it shows that the design of the module does not allow to exploit full voltage span of the DAC. The attainable signal reach could be probably higher with a different module design. Nevertheless, the capabilities of the module presented here are sufficient to test the array-forth code of the NFMIC system, and the array-forth code is the following topic of my presentation. Basic NFMIC system presented here is composed of 10 nodes. it might be tiresome to present a full code for all nodes. Instead of making my audience falling asleep, I will demonstrate on several short examples of increasing complexity how the port execution and other techniques can be exploited to program GA chips in an efficient and elegant way. Of course, the examples to be presented are all excerpts from the NFMIC system code. First, I will show how a port execution by call is used to divide workload between three nodes of the reception path. Then the modulator at the end of transmission path will be discussed, and I will show how to control it using a port execution by jump. The last example shows how to start and stop the oscillator without direct access to the node 715 using a port execution of a code delivered with a ganglion message. Before we start with the first example, one important remark regarding suspended nodes. When a node is suspended, there are basically two ways of waking it up. Either by an external stimulus, if the node has an access to a pin, at least a shared one, or by an activity at one of its ports. When suspended while reading a port, the node may await some data, which will be processed by a code stored in the node's memory, or it may expect a code to be executed out of that port. The distinction is crucial as the latter allows to change the course of code execution within the node without the node even noticing that if some precautions are observed. The first example shows a port execution used in a cluster of nodes at the beginning of the receiver path. As explained earlier, the node 614 controls the execution of code in nodes 714 and 713. The keyword in the node 614 is run. This word is executed when a data frame is expected. The first thing the word run takes care of is to prepare the whole cluster for reception. It starts with setting the B register to down port, which is the port shared with the node 714. Then it writes 1200D hex into the port. The almost cryptic number is a hex representation of an instruction word for a call to the address 0D hex. Thus, the node 614 wants the node 714 to start execute a code there. A boot descriptor of the node 714, this is a code that describes the out of reset state of a node, stores the left port address into the A register and the down port address, this is the address of a port shared with the node 614, into its instruction pointer. Thus the node 714 starts suspended, waiting for a code to be executed from its down port. And we know it's a call to the word pre. The word pre does some preparatory work, part of which is calibration of the ADC in the node 713. To this end, it writes 12019 hex into the left port. You may already guess that the number written to the port is a call instruction to the address 19 hex in the node 713. Also expectedly, a boot descriptor of the node 713 sets its instruction pointer to the left port. Thus, the node 713 starts execution of the word call. The word call first calls VSS to set an ADC to a negative supply voltage and then determines a count corresponding to that voltage. Then the word send writes the determined count back to the left port. This is the exact moment when the suspended node 714 wakes up and reads the value measured. The execution in 713 then returns to the left port and the node suspends again. Before the word pre in the node 714 comes to its end, it sends some data to the node 614 and then returns to the down port execution and suspends. The example just shown demonstrates the simplest use of a port execution. It allows to distribute a complex code between several nodes. In a way, it's just ordinary factoring, commonly used in Forth, with the difference that here we don't factor into words only. We factor the code out of a node into another one. The principle is the same. To sum it up, the port execution by call is the simplest method available. As it uses a call instruction, it pushes the return stack. Also, the word invoked in the target node must end with a return instruction. Although the port execution by call is suitable for almost all situations, there are moments when it cannot be used. The problem with this technique is that it affects the return stack of the target node. An alternative is a port execution by jump. This method is used in the second code example, showing an implementation of an amplitude shift keying modulator in the node 717. A boot descriptor of the node 717 sets the instruction pointer to 0. Therefore, the node starts execution from the word init right out of the reset. The code pushes 9 times a number 63 on the return stack and then jumps to the address of the right port. This is the port shared with the node 716 and suspends. In order to understand the meaning of the word init, I need to explain two concepts related to the F18 computer internals. Similarly to the parameter stack, the return stack has a circular design. There are 8 positions on the stack plus one top item in the register R. Pushing a value into the register R pushes its original contents onto the stack and discards the original bottom item. Pulling a value out of the register R pulls the value from the stack into the register, and at the same time it makes its copy into the bottom of the return stack. Another concept to be clarified is the for next loop. The word for is an array forth directive that compiles an instruction push and then it executes a word begin in order to mark the return address of the loop. Thus, when the loop is about to start, the top item of the parameter stack, this is the register T, is stored into the register R and the return stack is pushed down. The word next tests register R, and if the value is equal to 0, it is pulled out of the return stack, discarded, and the execution continues with the next instruction word. Otherwise, it decrements the value in the register R and jumps back past the push instruction. Now, notice what happens with a return stack fully prefilled with the same number. At the end of the loop, the stack is restored to its original state. Therefore, with a prefilled return stack, we can execute for next loops repeatedly without a need to push the loop parameter on the return stack each time the loop is entered. The source code for the loop is then a simple begin next clause. Let's return to the modulator code in the node 717. The two words that take care of a signal generation are mark and space. The word mark performs 64 cycles, where in each cycle it sets the DAC output to a predefined voltage and then to the ground. The switching of the analog output levels is controlled by a level change on the pin 17, which is internally shared with the node 715 running an oscillator. Thus, a carrier signal is generated. The word space works in the same way, except that it sets the analog output always to the ground. Combining marks and spaces creates the NFMIC signal. Now, notice the last instruction in words mark and space. It is a jump to the right port. Therefore, whichever word is executed in the node 717, eventually it jumps to the right port. Why? Well, in order to wait for a code from the node 716. The node 716's boot descriptor sets the register B to point to the right port. Therefore, whatever is stored through the register B is delivered to the node 717 and executed there. The two words taking care of this task are tick mark and tick space. The numbers set to the right port by these two words are hex representations of the jump instruction to addresses A hex and F hex, the addresses where the words mark and space are stored in the node 717's memory. Why don't we use a call instruction? Recall that executing the call instruction at a port first pushes the address of the port onto the return stack of the target node. However, we need to keep the return stack intact as there is a loop parameter. Executing a jump instruction circumvents this problem on the expense of an additional instruction word at the end of mark and space jump instruction back to the right port. When transmitting a frame, the node 716 receives a stream of bits, converts it into marks and spaces using the BMC algorithm, and instructs the node 717 to transmit them by jumping to the respective code through the port execution. While the mark or space is being transmitted, the node 716 has enough time to encode another bit in the stream and waits suspended until the node 717 jumps back to the right port, which immediately starts another execution of either mark or space word in the node 717. Owing to this design, there are no delays between marks and spaces transmitted. To sum it up, use the port execution by jump each time you need to avoid shuffling the return stack of the target node. Keep in mind, however, that the code executed in the target node must end with a jump to the port used for a code execution. Both variants of port execution, though useful as such, run eventually only a code stored in the target node's RAM. It only helps factoring a complex code into several nodes. Hence, the next example will show how to make a node run a code that is not stored in its own RAM. Instead, it will be delivered as a ganglion message. Before presenting the example, I'm going to describe shortly what a ganglion message is and how it is structured. A ganglion message is a means of communication between a polyfourth virtual machine and any other node of the G144 chip. When the message is delivered to a target node's port, it has two parts. The first one is a focus call to the port a message is being delivered to, in order to get an exclusive attention of the node. As the execution address is that of a port, the instruction pointer is not incremented and the next instruction to be executed will be read from the same port. The second part of the message is a payload, which are instruction words and data to be processed by the target node. When the last word is delivered, Ganglia waits for at least one word of reply from the target node. Now the oscillator node 715 starts execution out of the reset from the word go as is defined in its boot descriptor. It attempts to read the down port and suspends. In order to start the oscillator, it is sufficient to write one arbitrary word to the down port. The value is not important, but it allows the code to continue execution with the word clang. This word tries to drive the quartz crystal with pulses of different width and strives to find a resonant frequency. If not successful, it returns a non-zero value, hence passing through the if statement, and writes a 0 back to the port. The last action is to jump again to the word go. On the other hand, when finding the resonant frequency successfully, a 0 is returned, and the code continues past the then statement, drops the flag, and returns a non-zero value that corresponds to the width of the driving pulse. The execution then goes on, some preparatory work is done, and it eventually arrives at the word run. This is an endless loop that drives the crystal to keep it oscillating. At the end of each cycle, it tests the down port to see if we want to write there, and if so, it reads the word from the port, sends the word back, and jumps to go, which effectively stops the oscillator. The reason for sending the received word back is that the protocol for the oscillator control have to be the same whether starting or stopping it. One word written to the port and one word read back. The architecture of the NFMIC system does not allow a direct access to the oscillator node 715. As you will see shortly, port execution is an elegant way to solve this problem. The boot descriptor of the node 615 makes it to start execution at the word start, which after some initialization ends up attempting to execute from the up port and suspends. This allows to start any code inside the node's memory using a port execution by call. For instance, a code that assures transmission of data until the end of data signal is written to the port. However, it also gives us an opportunity to provide any other code from the outside of the node to be executed at the port. Not surprisingly, the code is delivered by a ganglion message. The message is presented as a source code here, including the focus call. Each part, separated by a slash, is compiled as a single 18-bit word. Green words are array-forth instructions. The white word is a placeholder for a port address. The instruction pointer, as well as the current contents of the port, are indicated for the sake of clarity. When executed, the code does the following actions. Fetch a word from the up port, that is, fetch the down port address and push it on the parameter stack. Store the address into the register A. Write any word from the parameter stack to the address pointed to by the register A, that is, to the down port. Fetch from the same address. Write the word just fetch to the port the code is executing from, that is, to the up port. Return to where you started from, which means return to the up port execution and suspend. As you can see, the node 615 performed all the actions needed to start or stop the oscillator. It has to be noted that the code is using both register A and parameter stack of the node 615 destructively and modifies it, because it does not harm the rest of the code used by the node. It's obvious that in other situations we would need to take some precautions not to disturb the state of the node. For instance, we would first store the contents of the register A on the parameter stack before using the register and then restore it before leaving. To sum it up, a port execution of a code delivered from the outside of a node, either via a ganglion message or supplied by a neighbor node, provides an extreme flexibility to GA chip programming. The code delivered by a ganglion message must end with a return instruction, and it must send at least one word back. I would also like to emphasize that the port execution of an external code is one of the methods how to deal with often criticized lack of memory in GA144. Actually, there's really no need for more RAM in a node, as the length of the code executed at a port can be practically limitless. A very nice example of a port execution is shown in a GreenArrays application brief number 4. Probably the most elegant port execution example I've seen so far is a code used in the Polyforth virtual machine for communication between the main processing nodes and coprocessors. I strongly suggest to read the chapter 2 of the product data book. In order to show how the NFMIC system works, I have prepared a simple demo application. A code in Polyforth sends in 1-second intervals a word of data to the transmitter using a ganglion message. Words delivered by the receiver are moved through wire node to the node 500. A code in the node 500 waits for a data word followed by an end of the data signal with all but sign bits equal to 0. Such a sequence represents data with a correct CRC. The GPIO pin of the node 500 is connected to a piezo buzzer. A simple code in the node 500 generates a beep whenever a correct data is received. When an incorrect data is received, either with corrupted CRC or due to an interruption of the transmission in the middle of a message, no beep is generated. In the following experiment, the audio signal proves a correct NFMIC link between the transmitter and the receiver under different conditions. The receiver module lays on the desk, while the transmitter module can be moved. It is wrapped into plastic foil in order to avoid any short contact. I place the transmitter in the proximity of the receiver and start the application. Beeps are clearly audible. When moving the transmitter module far from the receiver, somewhere around 2 inches, the signal stops. Moving the modules closer to each other restarts the beeps. The second example shows how the magnetic near field penetrates also a human body. Even if I place the transmitter module in my closed palm, the signal is still audible. The last example demonstrates how the near field can penetrate metals. Although I have wrapped the transmitter module into a piece of aluminum foil, the signal can still reach the receiver. This is a clear advantage of using the NFMIC in comparison with other RF-based communication systems, for instance Bluetooth. And this is the end of my presentation. I wish to express my acknowledgement to GreenArrays people and thank you for your attention.